Hello everybody, I'm Brian Cliffus from Cal Poly State University. I just graduated with my bachelor's in electrical engineering. So yeah, I'm going to talk about our spacecraft and also a survey of CubeSat communications that I did, that I wrote a paper about. At Cal Poly, we kind of have two groups in the lab. We have the PolySat group, which builds spacecraft, and we'll also do the Genso project, which we'll be talking about on Sunday morning, I think. And then there's also the CubeSat side of the house, which builds a P-pod and shake and bake and organizes launch opportunities and that kind of stuff. So those are kind of the two sides inside Cal Poly. Does everybody know what a CubeSat is? Yeah? Okay, good. Here's CP1 and CP2. CP1 was Cal Poly's first satellite. I didn't work on it too much. That was back before 2002.
It didn't actually fly because it was launched. It was lost in the Dnepr 1 launch.
And then CP2/CP4.
It was also on the Dnepr launch that crashed, but we had a flight backup, and it was reflown as CP4, and it was bus verification, and it mostly works. So I'll be talking more about that. CP3 also flew on the Dnepr 2 launch, and one's currently in orbit. It has two cameras, which you can see right there. They're cell phone cameras, about 1 megapixel each or so. And CP6 is going to fly pretty soon, supposedly in October, on a Minotaur. And it's similar to CP3, but with all the software bugs worked out. And it also has a plasma experiment that the Naval Research Lab is doing, and they're actually dropping it right on top of the cameras. So the whole payload is fitting in about 1.5 centimeters with cutouts for the cameras and the cables and stuff like that. And that's got it's got a couple tapes that are going to pop out that are 1 meter and 3 meters long, and charging them up to 300, 400 volts or something like that, and then they're going to measure the plasma as it travels through low Earth orbit. Here's an overview of our satellite. It's using a PIC 18LF6720, pretty standard. 3K of RAM, K of internally EEPROM, which we're not using at all. Ultra triple junction solar cells, about 30% efficient. Turns out we really don't need that. We could get away with probably dual junctions and be fine power-wise. And we use I2C at 100 kilohertz for all of our internal communications. It works pretty well. We have capacitance issues on the boards. So, yeah. There's our Earth station. We actually have two of them. The ISU 847 is hooked up to 2 meters and 70 centimeter Yagis up on the roof. And we use that for the Genso project right now, and also just for like a general use Earth station. And then the ICOM 910 is hooked up to dual-phased UHF Yagis for talking with our spacecraft. And we use Mac Doppler Pro for tuning the radios, etc. Works pretty well. Here's our transceiver. It's about 1 watt out in the UHF amateur band, but we can tune anywhere around there. And then change an inductor, and you can go up to 1 gigahertz. On the front panel, the balun for the antenna, low-pass filter. And then on the CND, command and data handling board, CNDH board, there's an AB switch for the 2 transceivers, and then various.
As for our transceiver, it works okay.
Future stuff, upgrade a 9600 baud, upgrade the transceiver chip. It's not designed for low data rates, close frequency separation. So the 1020 is. And then also the RF amplifier is no longer in production, so we have to build a new circuit for a new amplifier. CP3 in orbit right now and CP2, it's pretty deaf. Not quite sure why. There's could be several reasons why. Problems with the CC1000 or internal noise. We have a lot of stuff going on in a very small package, so it could be some switching power supplies or something getting into the way. And it's also spinning slowly, which means that we're spinning in and out of antenna nulls. Can't really help that besides spin up. Because of our software issues, we can't spin up at all or spin ourselves down. We added a 100-watt amplifier to try and correct some of these problems, but that really didn't help. We tried with an 18-meter dish at SRI up at Stanford in California, and it didn't help much. So something else is going on. And as a part of my senior project, I added a low noise amplifier to this spacecraft. 12.8 dB gain, 2.2 dB noise figure, and I'll talk about that more later. As we were doing just testing and trying to figure out what was going on with our spacecraft, we were looking around, you know, what do other universities use for their radios? And there really wasn't a single document that listed all the transceivers used in CubeSats. So I decided to write a paper about it, and I'll talk about that in the second half of the presentation. Here's our CC1000. You can notice this stuff right over here. That's all the connections to the PIC processor for programming all the register settings and output power and frequency and all that stuff. And that's also where the data goes in and out. So the PIC processor is very integral to this whole thing. It also does the TNC for it. And yeah, there's the CC1000, short range communications. The receive sensitivity, negative 80 dBm, not great at all. And that's what we're fighting right now. Downlink is fine. We're getting a watt out and we can hear it all the way down to the horizon. So downlink's not an issue. Uplink is. Should be reversed, but it's kind of weird. RF2117, up to 2 watts output power. We've got it turned down to about a watt just because we don't need the extra power. And 55% efficient, which is pretty nice. And there's the RF amplifier. This stuff right here, this is power. This is when you turn it on. You have to, it's a startup sequence for the amplifier. You have to get different voltages at different pins at different times, or the whole chip blows. Awesome. But there's the input from the transceiver, and there's the output, matching network, and all that kind of stuff out to the antenna. The low noise amplifier, which I added for my senior project, resides up here. Those chips up there. Problem that we had was that here's the transmitter going into the switch, and then here's the receiver going that way. There's only about 30 dB of isolation on the switch, and for putting out a watt, which is plus 30 dBm, and you only have 30 dB of isolation, you got about 0 dBm sitting right here on the input to your LNA. And the LNA is on all the time. So you're really blasting the LNA. It turns out we're okay because the maximum input to the LNA is plus 5 dBm. So we're okay, we're right on the borderline. We did a lot of testing. So we should be fine. And then that's also a high pass filter. So we just kind of have a quasi bandpass going on. And then that's the AB switch for the 2 comms, and then that's a non-inverting buffer for switching the comms off of one line. And there's more about the switches. Isolation is only 28 dBs. There's our antenna. It's cut a little bit short just because of the antenna route. So it's cut for 468 megahertz, but it works at 437, no problem. That's a low-pass filter, and there's the balun, and then the dipole. Okay, so this is about the paper that I wrote, Survey of CubeSat Communication Systems. I wrote it with Mr. Anderson and Kyle Levesque. Kyle's at SRI, and he graduated Poly a year and a half, 2 years ago. And Mr. Anderson's still at Cal Poly. And it's going to be published in the Amsat US newsletter pretty soon here. And it's also available online right now in draft form. So for satellite transceivers, there's really 3 ways of doing it. You can just buy a space-rated satellite transceiver. Even for CubeSats, those all are available. You could purchase a transceiver for terrestrial use and modify it for space use. And actually, that has been used successfully on many CubeSats. And then you can also custom build one, which is what we did on our spacecraft. So if you just want to purchase one, you can buy like a StenSat radio or a microhard MHX 2400. The microhard's not a great radio, but a lot of people like it in the States for some reason. It takes 1.15 watts on receive, which is tremendous amounts of power, especially for a CubeSat when you're looking at a 1 watt power budget, roughly, in total. So that's a lot of power. And it's also good if you have a really big dish because it takes a lot of power for the high data rates. And the SenseTime radio you can just buy. You can also buy a terrestrial radio and modify it and just take off the case, etc. A lot of the handhelds, the credit card Alinco radios have flown in space on the Japanese spacecraft, and so VX2R, a couple other radios. And you can modify the radios, thermal conductivity, etc., for the lack of air. And you usually have to add a TNC, but you can also just buy a regular TNC and stick it on there, and that works pretty well. And Q1, 1.7, all those guys, modified commercial radios. And custom built, I already talked about this a little bit. It's great for education because you learn a lot. Several manufacturers make all-in-one transceiver chips, or you could go the Delphi way and build your radio out of mixer parts and stuff like that. Yeah, Wooter, we'll be talking about that tomorrow, I guess, in the morning. Less successful. They haven't worked as well, just because we're not smart yet. I guess that's why we're still in education. So they don't work all that well, but I guess the Delphi's work fine, and ours works okay. And the latest launch, I didn't include these in this presentation, but they will be included in the paper. It went up on a PSLV in the end of April, and you guys probably already know a lot about it. All the satellites worked and are working. AAUSat-2 is a little bit deaf, but I guess they're getting through with it, with their big amplifier, and we'll hear from somebody in the team, probably Johan, on Sunday morning, I think. Compass 1 is also pretty chirpy, and that's got the characteristic sound. It's actually pretty cool to listen to. And then Q1.7 and Compass 1 were on the same frequency, coordinated for the same frequency. So not sure how that happened, but that's kind of fun to hear both spacecraft at the same time on the same channel. And here's just kind of overview of the radios. Used frequencies and power. Frequencies, mostly UH. And power outputs ranges a watt. And then a little bit higher if you're doing higher data rates, such as QuakeSat and AeroCube 2. Also, these spacecraft are organized by launch. The first one up here is the rocket launch in 2003. This is SETI Express. Q1.7 plus APD was launched on an MV8 out of Japan. GeneSat was launched on a Minotaur out of Wallops a year and a half ago or so. And these last satellites were launched on the Dnepr 2 just over a year ago. TNCs used, a lot of PIC processors and other processors. Protocols, mostly AX25, except for the proprietary ones on the integrated TNC and radio commercial ones. And yeah, SRLL is a protocol that was created by the Japanese. That's almost the same thing as AX25, but it includes error correction. So their spacecraft can all switch between the two. And the baud rates, mostly slow, 1200 baud, AFSK, 9600 baud, a couple of faster ones, AeroCube 2, GeneSat, and also the other microhard, which is MAST, which is a tether experiment. Data downloaded, this is kind of surprising. Oh, wrong one, never mind. Lifetime. A lot of the Japanese ones are still working today. 5 years later, which is amazing. And lifetime, also kind of interesting. In the beginning, we had ones that just never turned on. So another one right there. But as the more recent launches have shown, we can build spacecraft that actually work. The CubeSat community has grown up, and all the ones worked on the last 4 launches. All the CubeSats worked. Whereas the first 2 launches, some of them didn't work. So, and antennas are just various dipoles and turnstiles and stuff like that. Here we go. Here's the data downloaded. This is interesting. 456 megs total, 5 years. All the CubeSats here. And QuakeSat, that's the big number right there. So if you take out QuakeSat, we've downloaded 33 megabytes of data over 5 years, which is not a lot. So I think that kind of highlights the need for increased attention to the communication subsystems. A lot of people say that power is the limiting factor of CubeSats, but I'm going to argue that it's communications. So don't know about Sci5 or the German one, but you still, I mean, you're looking at, you know, half a megabyte, 10 megs, stuff like that. So that's kind of surprising. And when I was looking at all these different CubeSats, I came up with some different recommendations. Frequent beacons are really nice. The CubeSats in the beginning didn't have beacons, or they were very spread out once every 5-10 minutes, one packet. And that's really hard to tell if you're listening to the right satellite, really hard to find them. Luckily, people on the latest launch, the builders included lots of beacons, and all the spacecraft had beacons that ran almost continuously. And that's kind of nice. Common modes allow other stations to listen in and be a part of the action. That's pretty fun. I know that the Delphi guys, it's not a common mode, but at least you could plug it into your computer, and they've got a nice graphical display that shows exactly how their spacecraft is doing. And that has excited a lot of people, the Rascal program, and they've gotten a lot of data from that. So that's very helpful. AX25-1200 baud is also pretty standard for that. Operate ground stations regularly before launch. It's kind of surprising, but several of the CubeSats that have launched, their ground stations didn't work at the time of the launch. It's like, what do you launch on a spacecraft for if you can't talk to it or know if it's working, you know? So use your ground station a lot. It's kind of funny, but it happened. And there's also no really good consumer off-the-shelf solution. Does somebody want to build one? That'd be awesome. I know some people are working on it. And possibly use a ground station network. I'm going to be talking about Genso on Sunday morning, and that also has the potential to increase data downloaded tremendously. And that's all I got. Does anybody have any questions at all?